We need to show that for a particle in a rectangular well, that's in section 2.4, um, in the limit that the potential goes to infinity, equation 2.33 results in equation 2.20. So let me first write down equation 2.33. Um, yeah, so that is okay. So this is equation 2.33. Now we know that um, V0, in the limit that V0 tends to infinity, we need to find out what happens to this equation. So when V0 tends to infinity, E is going to be much, much smaller than V0, right? So in that case, we can potentially ignore this term goes to zero. We can consider that to be zero. We can also neglect the term E squared. So if we rewrite this equation, it will be sine of whatever's in there equals to V0 E times, yeah, we have this, it's a square root, so we just add that and cos of, whatever's inside. Uh, okay, so I got this by dividing both sides with V0, and uh, this side it goes to 1. Uh, and on this side, this goes under the root. And as V0 tends to infinity, this term tends to 0, right? So if now this term is equal to 0, then anything multiplied by 0 is going to be 0. So, and you can multiply both sides of the equation with -1. So it's going to be sine of something is 0, right? Okay, yeah. So sine of this term is 0. And what that means is whatever's inside, like we're taking sine of this term, right? So this term is equal to n pi. Plus or minus n pi, right? Now we square the equation on both sides. And that gives us 2me L squared over h bar squared equals n squared pi squared. H bar is basically Planck's constant over 2 pi. So squared would be h squared over 4 pi squared. So that implies we can write, now we can cancel this out on both sides. The energy becomes n squared, sorry, my bad. This is supposed to be h squared. Yeah. Okay, so this becomes n square, 8 square over 4 to the 8, ml square. So we have shown that in the limit that V0 tends to infinity, the energy becomes n squared 8 squared over 8 ml squared. And these are nothing but the energy levels of particle in a box. Okay, now moving on to part B of the question. So in part B, we need to show that the wave function of particle in a rectangular well converges to wave functions shown in equations 2.9 and 2.21 in the limit that V tends to infinity. So equation 2.9 shows the wave function that is in regions 1 and 3. And for a particle in a box, you have the potential V to be infinity, right, in both regions 1 and 3. So in that case, the wave functions in those regions for a particle in a box, they're going to be 0 in both of those regions. That's what equation 2.9 here gives you. And equation 2.21 tells you how the wave function inside the box behaves. And it is given by this. You can find V by normalization, but this is essentially what it looks like. Now we need to prove that the wave functions for a particle in a rectangular box actually converge to these three values in the limit that the potential tends to infinity. So let's first write down what the wave function in region 1, 2, and 3 looks like for a particle in a rectangular box. And that is given on page number 29. So psi1 is equal to C times exponential of 2m over h bar squared. Yeah, this is psi1. Let's deal with the wave functions in regions 1 and 3 first, and then we'll get back to the wave function inside the box. In 3, it is this. Okay. Okay, now we are saying that the potential tends to infinity, right? So let's examine psi1 carefully, right? As V0 tends to infinity, you have, that implies your exponential term has, well, a constant times infinity to the power half times x, right? So this is a very, it looks like it's a very high value, but what is the value of x? So you're looking at wave function in region 1, where your x is less than 0. Region 1 is where your x is negative, right? So here your x is negative. And what that means is you have the exponent of a very large negative value. That's what this means. And that would mean you have 1 over the exponent of a very large value, which would mean it is close to 0. So in the limit that V0 tends to infinity, your wave function is 0, right? Similarly, for psi3, let's see what happens. So your psi3 is basically exponential of negative a constant here and infinity, and you have an x, right? But psi3 is valid when your x is greater than L. So your x here is a positive quantity. So that means you have exponential of negative infinity. And that is something like this, which is 0, right? So psi 3 is also 0 in the limit that your V0 goes to. These are kind of easier cases to work with. Now let's go to psi 2. So psi 2 for particle in the box is given by equation 2.32, and that is A cos yes, this plus you have a cosine term and you have a sine term. Yeah. Now, based on continuity, so our wave function needs to be continuous, right? So what that means is the wave function at 0, which, so if you're taking the wave function region 1, the value of that at 0 should be the same as the wave function 2 at x equals 0, based on continuity, because we require the wave function to be continuous at x equals 0 and also at x equals L. And we already know that this term is equal to 0, right? So what that means is wave function inside the rectangular box at x equals 0 is also equal to 0. Now what that means is a times cosine of constant, your x here is 0, right? 0 is equal to b times sine of something multiplied by 0. Now, sine anything multiplied by 0 is 0, and sine 0 is 0. Right? Sorry, this is not equal. Yeah, this plus is equal to 0. Yes, that's your wave function. So sine 0 is 0. Cos 0 is equals 1. So what that means is a times 1 plus b times 0 is 0. That means your a is 0. So the continuity condition actually tells us that the value of a is 0. And what that means is psi 2 is basically just b times sine of this term, right? Now let's substitute for E. We found out that in the limit that V0 tends to infinity, energy is n squared, h squared over 8m L squared, right? Um, that means when you take the square root, you will get this. Now, we're going to plug this value into this equation, right? And that gives us to be b sine, let's see, here you have root 2m over h bar, which we can write as h over 2 pi, right? Multiplied by this, sorry, there's no square term. Yeah, nh over 2 root 2m times L over x. Now let's cancel out the 2m, and we can cancel out this 2, cancel out the h. And that gives us psi 2 to be equal to b sine n pi x over L. Right, we've got the terms, right? Pi x L. Yeah, so we have the wave function to be b sine n pi x over L. Now this is the same as what we have written down for particle in a box, right? So we have shown that in the limit that your potential goes to infinity, your wave functions of particle in the rectangular well converge to the wave functions of particle bonds.